Hi, my name is Muhammad Reza Irfan. So today I'm gonna demonstrate about our assignment one. For this one, we use the data from the assignment sheet. So there is a lot of data, which is there is temperature, humidity one, and etc. Next, we can see there is a plot of graph here. You can see the power output from the solar power. Okay, so we use this data to plot into our MLP, which is multi-layer perceptron. For this for this one, we use the Google Colab to train our data to predict the output from the actual data. Okay, so first we see the coding. You can see this our library we use import the pandas, numpty, and also the matplot library to plot our graph. And we also use the TensorFlow keras for the model layer and also optimizer. Okay, so next we can see this load data set. So which is we must load the sample of data to this Google Colab. So I'm gonna upload it, connecting the Colab to into the CPU. Then we upload. So this our CSV file. So you can get the clean data. Okay, so that this one we just copy the path, then we just paste it to the coding. Okay, so we're done. Paste the coding. So this code will read the file from here. Okay, next you can see the properties data from the column from the data. We see this column. We list out to this coding, and then we convert it to the column, and then filter it with which target of column we need to train. So this target from the column data. Then we target it to filter. Then we filter the data to generate the solar power here. Then we normalize the features. That's fit the transform feature scalar fit transform to normalize the feature. To filter after the data is filtered. Then we target it, the data to transform. Then we use this code to split the data set to 70% to train, and also valid to into the 30%. So you can see we split this value 0.3 with 30%. Then the random state is others from the others then 30%. Then we can define the function to compile the MLP model, this multi-layer model. You can see is the activation of ReLU. And then we have been given instruction to create a minimum two model. For the first model, we use the small hidden layer. So we can see there's two layer here, 32 and 16 only. Okay, two layer. Okay, so the number of layer is 32 and 16. Then another one layer is we use the large hidden layer. So we can see three layer. So this is 64, 32, and 16. Then this code will retrieve the both model. So we push it 100. Then batch of the data is 16. This train will take a few seconds to finish, and then we come out the output. So then after that we evaluate the data after the train. Then we predict the target. So there is model 1 and model 2 we predict after the train. And then we will plot the data into the graph. So this with the parameters for the graph itself for this figure size. So the first one is model 1 to plot into the graph, and also this model 2. Then we will save the both model into this file, and then we will save it after then plot out the graph, and then we'll save right here. Okay, so we try to start. Then just click on here, and just I can scroll and we see it process the code, and then you try to epoch for the first model until to 100. So if we use a large number of epoch, then it will take a few minutes to done the training. Then this one the second model to epoch, and then after that you can see there is we show that the loss, how many percent this loss after the train for model 1 and model 2. So this is a scatter plot for the actual versus predicted for both model 1 and model 2. So if you can see this model 1 first, the scatter plot, you can see the plot is nearest the ideal fit line. So this line is ideal fit line, which is it is most nearest the actual data. So this the blue one is just a predicted data, so it nearest the ideal fit line. So you can see the regression is like this. It's slightly almost near the ideal fit line. But for the model 2, we use the large hidden layer. So we can see after we done the training and then predicted the value. So you can see the scatter plot is more to down right here, and it not not it's not too far, it's not too far from the ideal fit line, but this regression show that uh, the data most likely going to down right here, going to the uh, not to not to exactly into the actual data. So the predicted is not too near the actual data. So this the scatter plot, and I want to show the other the others graph. I'm using the same code as right here. I'm using the same code. Then I just change the plotting the graph. Okay, this one I plot a different graph to show more clear line graph to see the difference between model 1 and model 2. So I run the code. So I try epoch for the first model. Okay, then continue to the second model. Epoch 100. Okay, so you can see both model are already trained, and you can see the loss right here is this one is less error than this one. Says 0.005, then this one is just 0.01. So there's a lot of difference. So you can see the first model, like the result before from the scatter plot. You can see the predicted plot is nearest the ideal fit line. So you can see this one also prove that this blue line graph is the actual solar, the actual data. Then the orange one is uh, the predicted value. So you can see you can see the age of this graph is almost near the actual data. So there is proof that the first model is less error than less less error to want to the data is less error from the actual data. That's we go to second model. the actual and the predicted data. So same as this model one, the blue line is the actual data. Next, the green line is the predicted data. So there's not to you can say that yeah, it's more different than the model one with the huge layer. Yes, so we can see there is such for example from right here, this age is not near the actual data, but this age from the model one is almost near the actual data. So there is a lot of difference between the model one and model two. So we can conclude that model one using the least two layer for the hidden layer to train the data is less error than the large layer that can show that the error is most likely the error is bigger than the least layer. So I'm done. So this my demonstration for our assignment. Then I can continue to the presentation from from my group teammate. Thank you. Okay, so I'm gonna continue to the slide presentation for our group 2 for intelligent control system assignment. Then this is my teammate for group 2. My name is Muhammad Rizal Irfan Muhammad Rizauddin. Then my teammate Eugene Yong TU, and also Muhammad Afiq Aiman bin Zulkifli. So I'm gonna go through to methodology from Muhammad Afiq Aiman, and result analysis from Eugene Yong TG. So I can continue.
Hello, my name is Muhammad Afi Aiman, and I'll present to you the methodology of this group assignment. So, for this assignment, in terms of software and datasheet, first, in order to simulate the multi-level perceptron regression model to predict the solar power output, we will be using Google Colab for its ease of use and versatility. And for our datasheet, it will be provided in the form of Microsoft Excel. And as you can see here, the data that we'll be using is the date, the year, the mean temperature, the humidity, the wind speed, global radiation, cloud coverage, irradiance from solar panels, temperature from temperature of the solar panel, and the 24-hour mean power generated from the solar panels. Now, for model programming and training, we by using the built-in functions in NumPy, TensorFlow, and others, we built two models, Model 1 and Model 2. So Model 1 was created with a small number of hidden layers, which is 2 layers, and each layer will contain 32 and 16 neuron layers respectively. For Model 2, it was created with 3 layers, which contains 64, 32, and 16 neuron layers respectively. For both models, they will run with a learning rate of 0.001. You can see here in the code screenshot. When we start training, both models will be trained for 100 epochs, a batch size of 16, and a verbose rate of 1. Now, after we've trained our model, we will be plotting the output of our model, and for this we will be using the function which is a matplotlib library. Okay, so for both models, the graph will be labeled as actual solar power versus predicted solar power. The predicted solar power for output for model 1, it will be colored in orange, and for the green for the model 2 it will be colored in green. So after the both outputs after we have both outputs, it will be then be measured and compared to determine which model will be more accurate. That's all for me. Thank you.
So this is the result for the model 1. So the plot compares model 1's predictions with actual output values from an A and N. So it generally shows acceptable predictive accuracy, as we can see uh, at this plot. Okay, it's accurate, aligning with the overall trend of actual values. However, it struggles with significant discrepancies at peaks and troughs, indicating difficulty in predicting extreme variation. So this model prediction are stable for most data point, but reveal challenges with data complexity in specific areas. Some deviation may be due to synthetic noise added for demonstration. So overall, Model 1 captures general trends but not sharp changes or outliers. So maybe due to its small architecture and potential underfitting. Okay, so this is the graph for Model 2. So, so it can also captures the overall trend and that the predictions show greater variability than Model 1 with noticeable discrepancies at peaks and troughs. So, this Model 2 is very sensitive to noise and struggles to generalize effectively. So, as you can see, Model 2's larger architecture 128, 64, and one output layer may contribute to overfitting, capture too much specific details from training data, and reduce generalization. So, uh, overall, Model 2 follows a general trend, as we can see, but fails to predict finer details accurately. Okay, so this is the scatter plot for Model 1 and Model 2 with actual output values from A and N. Model 1 generally aligns with the overall trend of actual value, showing acceptable predictive accuracy but struggling with significant discrepancies at peak and troughs. So the small architecture from Model 1, okay, 64, 32, and 1 output layer may contribute to an underfitting and inability to capture intricate patterns. So in contrast, we can see that here, Model 2 with a larger architecture, 128, 64, and 1 output layer shows greater variability and sensitivity to noise, but suggests overfitting and reduced generalization. So we can see that from this plot, Model 2 it follows a general trend, but it fails to accurately predict very fine details, while Model 1 can do it better. So, compare with the error analysis. So, the error from Model 1 are more stable but significant at extreme values, okay, as we can see at the outlier. So, while Model 2's errors are more variable, indicating an overfitting and sensitivity to noise. So to conclude, Model 1 is better suited for general trend prediction with stable noise sensitivity, with stable performance, sorry, while Model 2, despite it capturing more details, is less reliable due to overfitting and noise sensitivity. Therefore, Model 1 is preferable for applications during stable and general predictions, whereas Model 2 might be considered if uh, capturing finer details is crucial and noise can be managed.
That's all from our group. Thank you.